Welcome back. In today's video, we are going to be discussing what we're going to do with all of these chemical equations that we've been talking about. So taking into account that law of conservation of mass. So if you remember, the law of conservation of mass tells us the total mass before has to equal the total mass after a chemical reaction takes place. Whatever mass you have before has to equal the mass after. What that means is the total number of atoms of each element should be the same on each side of the chemical equation. If I have 6 oxygens on this side, I have to have 6 oxygens on this side because each oxygen atom has the same mass. So if I have 6 over here, that's 6 times the mass of oxygen over here. So to have the same mass, I have to have the same number of atoms of each side. So when we're dealing with the conservation of mass, we have to account for the total number of atoms on each side of the equation. And when that total number of atoms on each side of the reaction are equal, the reaction is said to be balanced.
So let's look at the combustion of ethane, which is C2H6, and oxygen gas that produces carbon dioxide and water. So this is our reaction. So when we start off, we have on the right side of the equation, or the left side of the equation, we have 2 carbon atoms and 6 hydrogen atoms in the ethane, and we have 2 oxygen atoms in our oxygen molecule. And then on the right side of the equation, we have our carbon dioxide, which is a carbon and 2 oxygens. And we have a water, which is an oxygen and 2 hydrogens. So, and you will notice that the reaction is not balanced because I have 2 carbons on this side and only 1 carbon on this side. I have 2 oxygens over here and 3 oxygens over here. And the different atoms all have different masses, and I don't have equal numbers of them. So I need to try and get this balanced. So I have 2 carbons on the left and only 1 carbon on the right. So I'm going to add another carbon dioxide over here. That's the only way I can get carbon over here, is to add another carbon dioxide. Well, that gives me another carbon on this side, but it also gives me 2 more oxygens, which leaves it also still unbalanced. So I've got my carbons balanced. Now I don't want to deal with the oxygens right now because they're kind of complicated. So let's look at the hydrogens. I have 2 hydrogens on the right side and 6 hydrogens on the left side. So I need to have 4 more hydrogens over here. And the only way I can do that is by adding some more water. So by adding 4 more hydrogens, adding those 2 waters, I added 4 more hydrogens, but I also added 2 more oxygens. And of course, it's still not balanced. But I just added 2 more oxygens. Over here I have 3, 4, 5, 6, 7 oxygens. I only have 2 oxygens on the left side. So I'm going to add a couple more oxygens. That gives me, I added 2 more oxygen molecules. That's 4 more oxygens total. Still not balanced, so let's go ahead and do another one. And that gives me, still not balanced, but now I have 8 oxygens on the left and only 7 on the right. Well, what do I do now? Well, okay, let's see if we can add some more water. So I'm going to add myself another oxygen, and so that gives me another water there, and that's 2 more hydrogens. Well, still not balanced because, well, over here I now have 1, 2, 3, 4, 5, 6, 7, 8 oxygens. I have 8 hydrogens, or oxygens on this side, sorry. But over here I have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens, and on this side I only have 6 hydrogens. The issue is the only way I can get more hydrogens on this side is to add another ethane. So that's what I do. The issue is, though, is by adding that ethane, I'm adding 2 more carbons and 6 more hydrogens over here. So obviously still not balanced, and now I have 4 carbons over here and only 2 carbons over here. So I need to add 2 more carbons. So to add 2 more carbons, I add 2 more carbon dioxides. That gives me my 2 more carbons, but it also gives me 4 more oxygens. Okay, still not balanced. But now I also have that 12 hydrogens on this side and I only have 8 over here. So I need to add 4 more hydrogens. So I add my 4 more hydrogens. That gives me, by adding 2 more waters, it gives me 4 more hydrogens, but it also adds 2 more oxygens to this side. So now my hydrogens have the equal number on each side. I have 12 over here and I have 12 over here. My carbons, I have 4 over on the right side and I have 4 over here on the left side. But my oxygens, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And on this side I only have 1, 2, 3, 4, 5, 6, 7, 8. So I need to add 6 more oxygens. And I do that by adding 3 more oxygen molecules. And when I add those 3 more oxygen molecules, that adds 6 more oxygens to this side of the reaction. And now the reaction is balanced. Each side has an equal number of atoms of each element on each side of the reaction.
So after we balance the equation, we then have to write it down, and we write down the skeleton equation. And when we're writing these chemical equations, we have to balance them so that they reflect that law of conservation of mass. We can't just say we have this compound plus this compound makes this compound plus this compound. We have to actually account for the balancing, the number of them, and we do that with the coefficients. And a balanced equation is one of the most important tools in a chemist's bag of tricks. Without a balanced chemical equation, there's a lot of things that we cannot do, and most of the things that we do have to have a balanced chemical equation before we start. So when balancing chemical equation, there is one unbreakable rule. Never, ever, ever change the chemical formulas. Only the coefficients. Remember, those coefficients are the numbers out in front, not the little subscripts. We can only change the coefficients. We cannot change these subscripts. We cannot change the chemical formulas because that changes what chemical we're talking about. So we change the coefficients. These coefficients tell us how many there are. So in the example we saw a few minutes ago, we ended up with 2 ethane molecules sitting there. And so the coefficient there was 2 because there were 2 of them. There were 7 oxygen molecules, so that coefficient was 7. And that's 7 times 2 because each molecule had 2 oxygens, gave us a total of 14 oxygens there on the left side of the equation. So those coefficients are what we cannot change, or what we can change. We cannot change the subscripts. Now, there is not a step-by-step process to this skill. I can't say step 1 do this, step 2 do this, step 3 do this, because every chemical equation is different. Every chemical equation is going to work out a different way, but there are some common things that you can look for, some similarities. So there are some helpful hints that you can learn to follow and to look for, things that you can look for to help you balance this equation, balance equations in a more quick and easy way. But what you need to understand is that this is a skill. It's a problem-solving skill. Taking information that you have and looking for ways to solve the problem. It's not necessarily a one only this type of situation skill. It's a skill of problem solving. So practice your problem solving skill. These are puzzles. So let's look at some of these helpful hints. 1, always balance lone elements last. If you have an element that is by itself and it's not part of a compound, balance it last because you can balance everything else first and then come back and balance that by simply changing its coefficient really simply. Because one of the problems and difficulties of balancing equations is that when you change the coefficient of one compound, it's going to affect all of the others as well. You'll see that when we do the examples in a few minutes. Another helpful hint is when water is one of your substances, balance hydrogen and oxygen last if possible, because water, H2O, is always going to affect all the other things. So you balance everything else first and then go back and balance your hydrogens and oxygens. Because if you balance everything else first, sometimes all you have to do to balance your hydrogen and oxygen is change the coefficient of water. So when water is part of your reaction, try and balance everything other than the hydrogen and oxygen first. A third helpful hint is if you have a polyatomic ion and it does not change from the left to the right side of the reaction, treat it like an element instead of separating it into its elements. So if you have something like sulfate, SO4, if you see SO4 on the right side of the equation and SO4 on the left side of the equation, then treat SO4 as if it was an element instead of treating it as sulfur and oxygen. It just makes the counting easier. You could separate it into the elements if you want. That is totally doable, but oftentimes treating the polyatomic ions like an element will make the balancing go a little bit smoother. Now, when you have an even number of atoms on one side of the reaction and an odd number of atoms on the other side of the same element, multiply all coefficients by 2 and work from there. And the reason you do that is because if you have an even number on one side and an odd number on the other side, it's very difficult to get them to work together and become balanced. But if you multiply everything by 2, what that does is takes all those odd numbers and makes them even numbers. And so it makes the balancing a whole lot easier oftentimes. When you have everything balanced, make sure to reduce your coefficients to the lowest possible ratio. If you end up with coefficients of 2, 4, 6, and 8, all of those can be divided by 2. So you need to reduce them because the correct balanced equation is always going to be the one with the smallest ratio of coefficients. So if you end up and you get it all balanced and it's 2, 4, 6, and 8, you need to reduce those to 1, 2, 3, and 4. So that you have to have the smallest possible ratio. That is the correct way to do it. Now, if you have water on one side of the reaction and hydrogen compound or a hydroxide compound, on the other side. Remember, hydroxide is one of our polyatomic ions. So if you have water on one side and hydroxide on the other side, then rewrite your water to be hydrogen hydroxide, HOH, and treat that OH of your water as a hydroxide and the H of your water as a individual hydrogen. You'll see examples of that in a few minutes, but it makes the balancing a whole lot easier if you treat water like hydrogen hydroxide instead of dihydrogen monoxide. So separate your water or treat your water like HOH whenever you have hydroxide compounds. All right, so now we're going to get into the examples. So for our first example, we have the word equation and the skeleton equation. We have manganese 3 carbonate is going to produce manganese 3 oxide and carbon dioxide. And you'll notice that I have the skeleton equation written out with blanks here in front of each of our compounds. Now, once we have the skeleton equation written, we cannot change any of the formulas. The only thing we can change are these coefficients. Right now, I don't have anything written in the coefficient blanks, and we're going to fill that in as we go. So the way that I like to do this is right here underneath the arrow, I'm going to write down all of the elements that are involved. We have manganese, we have carbon, and we have oxygen. So those are all of the elements that are involved. Now on the reactant side, on the left, we have 2 manganese, and there's 3 carbonates, and each one of those, there's 3 of these carbonates, and each carbonate has 1 carbon. So you'll notice I'm going to take the subscript and multiply it by how many things there are in there. So one thing you need to make sure you remember when you're looking at this, the subscript applies to whatever is immediately to the left. So this 2, immediately to the left of that 2, is manganese. So that 2 refers to the manganese. This 3, immediately to the left of the 3, is the parentheses, which means this 3 applies to everything inside the parentheses, so we have to multiply. So that means there's 3 times 1 is 3 carbons, and then 3 times 3 is 9 oxygens. Okay? So then on the right side of the equation, I have 2 manganese and I have 3 oxygens here, but there's 2 oxygens here. So we have to look at the entire side of the equation. So I have 3 plus 2 is 5 oxygens. Excuse me. And then my carbons, there's only 1 carbon. So the manganese are balanced. That's good. The carbons and oxygens, however, are not. Now what you'll notice is that there are oxygen in 2 different compounds on the right. So I don't want to deal with the oxygen right now. If I balance the oxygen, I have to do that in a weird way because there's 2 different compounds that contain them. So what I'm going to do is try and balance the carbons first. So to do that, if I have 1 carbon on the right and 3 on the left, I need to have 3 carbons over here. So what I'm going to do is I'm going to put a 3 here. So this coefficient now multiplies everything here. So I have 3 times 1, there are now 3 carbons on the right, and 3 times 2 is 6. So that's 3 times 2 is 6, but I have to remember to add those 3 also. So 6 plus 3 is 9. And amazingly, what you'll see is I have 2 manganese, that one's balanced, 3 carbon, so the carbons are balanced, 9 oxygen, the oxygens are balanced, so the entire equation is now balanced. I have the same number of each element on the left and on the right, so it is now balanced. Now, if you're just writing out the skeleton equation, we would leave this as it is. But when you're filling out a worksheet or you're filling out a paper and there are blanks, oftentimes you're going to need to fill in the blank. So we're going to fill in the blank with a 1 because that's understood to be it. So it's 1 manganese, 1 manganese 3 carbonate, 1 manganese 3 oxide, and 3 carbon dioxides. So that is what this is. This equation is now balanced, and so let's move on to the next example. All right, so for this example we have lithium hydroxide is going to react with phosphorus acid and is going to produce lithium phosphate and water. Now, this one is going to show a couple of those special little tricks that we mentioned before. So let me just talk about it. And as we see, so we've got lithium hydroxide, polyatomic ion, phosphorus acid, so phosphite is a polyatomic ion. And so we have, notice you have PO3 over here and PO3 over here. So the phosphite stays phosphite. So whenever I'm writing down what is involved, I can do it as elements, or I can make my life a little bit easier by keeping the polyatomic together. And I'll show you what I mean by that in a second. But you also notice that you have hydroxide on one side and water on the other. And so you have hydrogen and hydroxide and water on the other side. So what I'm going to do is I'm going to pretend that that water is hydrogen hydroxide. That is totally okay. That is another possible form of water. So I have hydrogen, I have hydroxide, and I have phosphate and lithium. So that's the elements that we're going to write down here. We have lithium, and then there's hydroxide, and I'm going to treat hydroxide. Every time I see OH, I'm going to treat it like a element, and then I have hydrogen, not the hydrogen that's part of the hydroxide, and then I have phosphite. So you'll notice I wrote down the formulas of the polyatomic ions down here, and I'm treating them like a element in this case. So on the left side of my equation, now it's time to balance. On the left side of the equation, I have 1 lithium, and there is 1 hydroxide. There are 3 hydrogens. Now again, there's a hydrogen there, but that hydrogen is part of the hydroxide. So I'm only counting the ones that are not part of the hydroxide. So I have 3 hydrogens here, and then there's 1 phosphite. Again, a lot of people think that, well, there's 3. No, there's 3 oxygens in that 1 phosphite. So remember, phosphite is a polyatomic ion. There is only 1 phosphite there. There is only 1 phosphite here. So on the right side of the equation, we have 3 lithiums. There is, remember I'm thinking of my water as HOH, so there is 1 hydroxide. There is 1 hydrogen. Again, this is the hydrogen that is not part of the hydroxide, so there's 1 hydrogen there. Excuse me. And there is 1 phosphite. So now, in order to get this to be balanced, I have
my hydroxides and my phosphites are already balanced. My lithium and my hydrogens are not. So I always like to do the things that are not part of water first. So hydrogen is part of water, so I'm going to balance my lithiums first. So I have 3 on the right, 1 on the left. So I'm going to add, I'm going to multiply this one by 3, so that gives me 3 lithiums over here, but it also multiplies my hydroxides. So I have 3 hydroxides on the left now also. So it balanced my lithiums, but it unbalanced my hydroxides. So let's balance our hydroxides now. So now I have 1 hydroxide on this side, so I'm going to put a 3 right here, giving me 3 hydroxides. 3 times 1 is 3 hydroxides, but it also gives me 3 hydrogens. Again, I'm going with the hydrogen hydroxide here instead of the H2O as I multiply this out. All right, so you'll see now that I have 3 and 3, so my lithiums are balanced. I have 3 and 3, so my hydroxides are balanced. 3 and 3, so the hydrogens are balanced. 1 and 1, so the phosphites are balanced. So now I'm going to fill in my blanks with 1s just so that I have something in all of the blanks. And so I have 3, 1, 1, 3 are my coefficients of this balanced equation. You'll notice that all of them have the same number on the left that they do on the right. That is the goal. All right, so for our third example, we have sulfur trioxide is going to break down to produce sulfur and oxygen gas. And you'll notice that when I wrote the skeleton equation, sulfur is one of our polyatomics that is going to get a subscript of 8, and oxygen is one of our diatomics that will always get the subscript of 2. So sulfur trioxide, notice that I did not give them the same subscripts here because sulfur trioxide, this is the formula for sulfur trioxide. These are because they are their element forms and they are separate. And those are the special ones. So let's look at the elements. I just have sulfur and oxygen. That's all that's involved in this reaction. On the left side, I have 1 sulfur and 3 oxygens. On the right side, I have 8 sulfurs and 2 oxygens. So I need to get an equal number of sulfurs and oxygens on each side of the equation. So I usually like to deal with oxygen last, that's just the way I do things. So let's balance the sulfurs. If I have 3 or 8 sulfurs here and only 1 sulfur here, then I need to multiply this by 8. So I'm going to multiply that by 8, and that gives me my 8 sulfurs. But it also gives me 8 times 3 is 24 oxygens. So I have my 8 sulfurs, so we're good there, but I have only 2 oxygens. So I need this to be 24. So 2 times something has to equal 24. Well, that would be 12. So 2 times 12, I now have 24. And my sulfurs are now balanced. My oxygens are balanced. And so I'm going to fill in my blank with a 1 just so that I have a blank filled in. And there is my balanced equation. This one's not that complicated. However, it becomes a whole lot different if you forget to do these subscripts when you are writing your skeleton equation from the word equation. So make sure that you always remember those 7 diatomics and those 2 polyatomics that we talked about in a previous video. All right, let's do another example. Okay, so for this example, we have potassium nitrate decomposes to produce potassium nitrite and oxygen gas. So a lot of people would be tempted to keep the polyatomic ion together, but you'll notice that I have NO3 here and NO2 there. Those are not the same. So we cannot keep the polyatomic ion together on this one. We have to separate them because they're not the same. So I'm going to treat the elements. We have potassium, we have nitrogen, and we have oxygen. So on the left side of our equation, we have 1 potassium, and there is 1 nitrogen, and there are 3 oxygens. And on the right side, we have 1 potassium, we have 1 nitrogen, and we have 2 plus 2 is 4 oxygens.
So this is that situation where we talked about these two are already balanced, these are not. And the issue here is we have an O2 here. That's an even number, so whatever I put here is going to get multiplied by 2 to give me an even number. Well, I have an odd number on this side and an even number on this side. So really the only way to reconcile that is to multiply everything by 2. So what I'm going to do is I'm just going to put a 2 in every single blank. That's to get rid of the odd-even discrepancy here. We have odd on one side and an even on the other. So when I do that, that's 2 times 1. I now have 2 potassiums, 2 nitrogens, and 6 oxygens. I multiplied everything by 2. And so I have 2 potassiums, 2 nitrogens, and this is 2 times 2 is 4, plus 2 times 2 is 4, so there's 8. So you'll notice that I have multiplied everything by 2. These two are still balanced. So I don't want to change these, because if I change these coefficients to get my oxygens to balance, that's going to mess up my potassiums and my nitrogens. So I don't want to mess with the elements or the coefficients of the compounds that have potassium or nitrogens, but I have oxygen over here. Oxygen's the only thing that's not balanced, and I have oxygen by itself. So I can change this coefficient only and not affect the other two. So if I have 6 on this side and 8 on this side, I need to get 2 more over here. Okay? So instead of having all of that, let me take this. So I have 4 here and 2 here would be 6. So I'm going to change that to a 1 instead of a 2. So now I have 2 potassiums on each side, 2 nitrogens on each side. I have 6 over here. 2 times 3 is 6. And I have 2 times 2 is 4, plus these 2 is 6. So I've changed that to 6. And so now everything is balanced. We are good. And it was just a little process of knowing when to multiply by 2, and then of course undo that a little bit for just one of the elements. And so that is our next example. So let's move on to doing another example so we can get some more practice. Okay, for this example we have water plus dinitrogen trioxide will produce nitrous acid. So no polyatomic ions or anything. We're just going to write our elements down. We have hydrogen, we have oxygen, and we have nitrogen. Those are the elements that are involved. And on the left side of our arrow, we have 2 hydrogens. There are 2 nitrogens. And I have 1 plus 3 is 4 oxygens. And on the right side of our arrow, I have 1 hydrogen, 1 nitrogen, sorry, I wrote that in the wrong place, and 2 oxygens. Okay, so this should be fairly easy to see that this is double the other side. So 2, 4, 2, 1, 2, 1. So all I need to do is double this side. Well, since there's only one chemical over here, there's only one product, then all I have to do is simply double that side, and that gives me 2 hydrogens, 4 nitrogens, or sorry, 4 oxygens. 2 times 2 is 4, and 2 nitrogens. So 2 hydrogens, 2 nitrogens, 4 oxygens, and that is now balanced, balanced, balanced. So I would just fill in my blanks with 1s. That one was a fairly simple one. So let's go on to another example. All right, so in this example, we've got quite a bit going on here. We have calcium hydroxide plus phosphoric acid is going to produce calcium phosphate and water. So we have quite a bit going on. We have polyatomic ions in all of them. We have hydrogen, or an acid on one side, and a hydroxide and water. So I have hydroxide and water. So a couple of our tricks are going to go along here. So I have calcium, and then hydroxide is a polyatomic ion, so I'm going to keep it as a polyatomic ion. I have hydrogen, that's part of that acid, and then I have phosphate, PO4, and it stays PO4 on both sides of the equation. And because I have hydroxide and hydrogen and then water, I'm going to treat my water like hydrogen hydroxide like we did before. So let's look at this. We have 1 calcium on the left, and there is 2 hydroxides, 2 times OH, so there's 2 hydroxides. I have 3 hydrogens and 1 PO4, so there's only 1 phosphate there. Now on the right side of the equation, I have 3 calciums and 2 phosphates, and then there is 1 hydrogen and 1 hydroxide. So again, it's always best to try and balance your waters last, because sometimes by trying to balance the hydrogens and the oxygens in the water, you mess up everything else. So we want to balance just the calcium and the phosphates first, would be the easiest thing to do, and then we can deal with the water. So I have 1 calcium and 3 calcium, so I know I'm going to need to have 3 calciums on the left, and that is going to also multiply this. 3 times 2 is going to give me 6 hydroxides. All right, so my calciums are now balanced. So let's go ahead and balance our phosphates. We have 2 over here and only 1 over here. So I'm going to need to get 2 on this side. So when I do that, it's 2 times 1 phosphate gives me 2 phosphates, but it's 2 times 3 is 6 hydrogens. Okay, so now you should be able to see my calciums are balanced, my phosphates are balanced, and you should see that this hydrogen and hydroxide are each 6, and on this side, hydrogen and hydroxide are each 1, and notice we have here hydrogen hydroxide. So I simply need to multiply this by 6 to give each of these 6 to make them balanced, and now my entire thing is balanced, and I'm going to fill in my blank with a 1. So my coefficients are 3, 2, 1, 6. Now that you have seen multiple examples on how to do it, hopefully you can go back and look at those setups, the helpful hints, things to look at and things to see and look for. But really this does take practice. It takes lots of practice, and the more you practice it, the easier it gets. So make sure you practice it so that you can get this down, because the balanced chemical equation, as I said earlier, is the best, most important tool for a chemist. Moving forward, as we go on and we learn more stuff, you will see that one of the first steps to everything that we're going to do is to have a balanced chemical equation. So you need to make sure that you know how to balance them and balance them properly, so that you can always start off with a balanced chemical equation and then solve your problems much, much simpler. All right? So, thanks for watching. Have a day.